So of all the stuff in the universe that matters, we are in that little slice. This is new. This, Ralph Alpher and Gamow and Robert Herman, they did not know about this. They thought, I mean, there's, you know, obviously our knowledge has expanded. They thought that the Big Bang nucleosynthesis that they calculated quite accurately, we covered this last time, they calculated how much of the universe should be helium, 25%. How much should be beryllium, a tiny fraction, and so forth. They did those calculations. Those have been improved over the decades. But it wasn't until very recently that we have this pie chart. This is new. I'd say 25 years ago. How to interpret the cosmic microwave background data and tease out this result. Yes, sir?
So is the net energy of the universe zero?
It is. So that's something else we should say. The total energy of the universe is zero. If it weren't, we wouldn't have a flattened universe. So you say, well, how can that be? I mean, the universe is full of all this stuff, and we're counting. Everybody has seen this. So if we have electromagnetic radiation or mass, like electrons and humans, it all goes in the same bucket. We convert the mass part using this famous formula to get energy. And then the light in the universe flying around, the light from stars and galaxies, that's energy too. And the early universe, back here, it was all light. Light photons is the way we deal with it. All this was, mostly, say 70 or 80% of the energy in the universe at that time was light. As the universe has evolved, that's changed. The density of, because the universe has expanded, the density of light, its influence in the evolution of the universe has been made smaller. But dark energy, dark matter, now completely dominate what's going on. 95% of what's happening is dictated by this curve, or this pie chart. Yes?
How do you define dark matter?
We have time to talk about this. Let me tell you about Vera Rubin, famous woman, obviously, woman astronomer, who had a professor named George Gamow. I think he was at Georgetown University when Vera Rubin did her PhD, and he kept saying to her, "Yo, this is not going to work out, Vera." She had 2 kids when she met him. I think she had 2 more kids while she was a graduate student, and it was like mayhem. She was a student and had kids. But here's what she noticed. Well, we start by looking at the properties of our solar system. This is distance, and this is velocity, and I'm going to show you where the planets lie on this curve. So Mercury's here, and Venus is here, and Earth, and Mars, Jupiter. I don't know why that happened.
Software change required.
Oh, well, we'll just not change our software. So it turns out, and Kepler, back in the 1640s, knew this. Remember I told you when his friend Tycho Brahe was dying, Kepler was in Germany and Tycho was in Denmark, Kepler went and, I think even before Tycho died, Kepler went and took the data, put it on his pony and left. Because he trusted that Brahe had looked at the stars with primitive telescopes in his eye, and he had measured the positions of the planets extremely accurately. And Kepler's trying to figure out, how's this all happening? What are the properties of motion? And he came up with laws. One of them is this, that there's a formula that describes the velocity of objects orbiting the sun as a function of their distance. So then when we got into say, the 40s and 50s and people were looking at galaxies, they expected that if you look at, here's distance, and velocity. If you looked at stars moving in a galaxy, you would get this. But you don't. Vera Rubin was the first to find this. Looks like this. This is a puzzle. And there are 1,000 different astronomers that try to work this out. The theory that works best is, here's a galaxy that rotates, and there's a flow of stars. It takes 200 million years or something for our galaxy to make a rotation. That there's something in here that we cannot see. If you take a picture of this galaxy, you do not see there's additional matter here, and it's thought to be kind of a big cloud, kind of spherical, and it's dark matter. We don't know what it is. That's a Nobel Prize waiting to be won. And if the distribution of matter is right, you get this curve. You get this curve.
What, is it undiscovered part, perhaps?
We don't know. WIMPs, one of the possibly WIMP. Can't take a phone call now. We're explaining the universe. This says weakly interactive massive particles. So there's a candidate solution. WIMPs. That's a Greek letter nu, frequently used in physics to describe neutrinos.
So something like a neutrino, maybe?
Every time they study the mass of the neutrino, they discover its mass is even smaller than we thought. For neutrinos to be this cloud, there gotta be a lot of them. Now here's what's interesting. If you postulate dark energy floating around in a galaxy, you can explain this curve. But there are people who say, that's poppycock. It just can't be right. There's no such thing as dark energy. So then you have to ask them, well, how do you explain this? When we look at distant galaxies, we can see light curvature of the path.
And nothing there.
And there's nothing in between. Nothing that we can see. Nobody knows what to do about dark matter. And dark energy is even weirder. Here's the way it works. When the universe expands, if you take a balloon, you have some air there, and you somehow make it expand, like you drive from Fort Collins up to the top of Long's Peak, pressure's lower, the balloon will get bigger. Pressure inside, the number of molecules inside holding the balloon erect, that hasn't changed. It's the outside pressure that's changed. That's not the way it works with dark energy. When the universe expands, it has more volume. And that more volume invites dark energy to be born, which makes it expand, and then more dark energy appears, and it appears like the dark energy will fill the vacuum that you would have expected. So it's like we take the balloon from here, go up to the top of Long's Peak. If the balloon is bigger, the pressure is lower. That's how it gets bigger, because the outside pressure is lower. Dark energy seems to be an infinite supply of it. And the bigger the universe gets, the more there is. And I'll tell you now that there's a theory. You can go to a lab and try to measure how much energy is in an empty box. And back in 1948, Casimir, I'm sorry, this pen is useless. Casimir, a Dutch scientist, did a calculation. How much energy is in an empty box? And he got a number that's not zero. It has to do with the way quantum particles, virtual particles, appear and disappear all the time. It's happening in this room right now. As long as they don't stick around very long, they can pop into existence and then disappear. So Casimir, there we go, he did a calculation in 1948 and calculated how much energy is in an empty box. And people famous physicist, I think Enrico Fermi, said that guy's nuts. There's no energy in an empty box. And if we have time, I'll show you how he proposed an experiment. This is what real scientists do. They don't just make up ideas. They say, I have an idea, and here's how you can test it. Well, it took from 1948 to about 1985 to have technology enough to actually measure what Casimir predicted. And he was right. You get the right number. Here's the problem. If the universe had that much energy in an empty box, you take everything out of there, the universe would have gotten so big, so fast, that we would not be here to talk about it. His theory works, we know, because we go in the lab, we can measure what he predicted. The problem is, we've also measured the amount of energy that's in a box of empty space out there among the stars, and his theory misses explaining what's going on by that number. Just something wacky going on there. So let's carry on with the lecture. Oh, okay. Now, see the 5% I've circled up there? I want to remind you of something. I showed you this in the second lecture. So last week we talked about the early universe, and we said we can, using the techniques developed by Ralph Alpher and Robert Herman, we can predict the concentration of different elements as they should have been formed in the early universe. And here they are: deuterium, helium, lithium. And we have these curves, the red curve, the blue curve, and the purple curve, and we can slide this vertical bar. We want to find a place where all the theories match. If we slide the bar, here we go. We got, this is, the horizontal bar is what it's been measured. So the orange bar and this blue have been measured, and purple's been measured. And if you slide this vertical bar back and forth, and you find a happy place where the theories match, this number is how much of the universe is us stuff. 4%. The previous curve said it's 5%. We're on the right track. See that? The 5% there comes from the microwave background measurements. This, kind of like 5%, comes from measuring the quantities of different elements found in galaxies by looking at millions of galaxies. Another thing graduate students do. Look at the right computer programs to analyze the light coming from distant galaxies and figure out how much of that is helium, beryllium, lithium, and so forth. 5%, kind of like 5%. We're seeking something called concordance, where we have multiple different ways of looking at the universe and they all agree. See, there is a little problem there with lithium. People are working on that. See, so that little ellipse that just appeared, that's pointing out that as soon as people did quality work on the topic that Ralph Alpher started and got 4%, they started to think, oh, wow, if the universe is 4% us stuff, what's all the other stuff? That was like 40 years ago, and now we know it's all about this. The universe is almost entirely not us stuff. Now, there's an issue. Let's go back. We talked about, early in this lecture, I'm sorry, we're going backwards. Look away if you get dizzy. If you get dizzy easily. Early universe is in here somewhere. Come on. It has to be here. Go back to page 1. Oh, I apologize. The amount of neutrons. Oh, I talked about it, but I didn't show a graphic. Okay, so here's something I just learned about. This is from a year ago. Remember, one of the things I said our first session together is I want you to be aware of the emerging issues in cosmology. Because you can read a book, even a book published today, the content was produced 3 years ago or something. Some stuff has happened we don't understand. So I mentioned to you that neutrons are not stable. If you take a bunch of neutrons and put them literally in a physical bottle, we could do this, and you measure how many neutrons are in there over a period of time, the half-life of neutrons is about, there it is, 15 minutes. But it turns out there's another way to do this, and that is to produce a beam of neutrons and do the same kind of measurement. So they're moving through, the beam means they're moving through the laboratory. They're moving from a source of neutrons through some kind of an experiment. You don't get the same number. It's a 9-second difference. This has just come into focus over different groups around the world making bottle and beam measurements. Nobody knows why there's a difference. And it matters. Here's the data. So the beam results, now these are in number of seconds. So the average for the beam results is here, and the average for the bottle results is here. And people, this is over a period of the last 30 years. People have made their measurements better and better along the way. The error bars were here, and then they get smaller, generally getting smaller as the experiments get better. The average is here. There's that difference. And it matters because we've talked about this before, actually last week. The number of neutrons available in the early universe dictates how quickly hydrogen becomes helium and lithium and beryllium. So this is more data on the topic. Oh, here's the curve I was looking for. So you've seen this before. Here's the very early universe. There's 1 second. After 1 second, remember this point right here is 100%. Almost the entire universe was hydrogen. And here are the neutrons. Now, this slope of this curve is because neutrons decay. If you just take a bottle of neutrons and leave them alone, they slowly get fewer neutrons. Right here, they really got gobbled up because atoms started grabbing neutrons and forming from helium, from hydrogen, started forming helium, that's the curve that goes right there, and deuterium, which is heavy hydrogen, and tritium here, and beryllium and lithium. So this is understood why this slope is so steep, because neutrons that were available started getting captured in the nucleus of hydrogen and producing isotopes of hydrogen, and other nuclear chemistry happened. But this curve right here could be wrong. Nobody knows why. So there's the University of Connecticut apparently is a world leader in this. They've redesigned. Here, I'll give you an example of what they did to try to fix the problem. They said their early experiments had literally a physical bottle filled with neutrons, and they were measuring the decay rate. How do they do that? They exploit the fact that protons are charged particles, and you can, just like electrons, except with an opposite charge. So if you have some kind of electronic measuring device, when a neutron becomes a proton, and then there's other stuff produced, they can count the number of protons because protons are charged particles. Neutrons are uncharged. So they could fly past you, you wouldn't even know. But protons will interact with like an electric counter. So you can measure this. So people said, Connecticut, you're doing it wrong because you have a physical bottle. Some of those neutrons could be hitting the wall of the bottle and getting stuck in the wall or bouncing off the wall in weird ways. So they reinvented their experiment. They got rid of the bottle and they made a container out of magnets, out of magnetic fields. So when they create a cluster of neutrons, the neutrons are trapped just levitating in space because they have electromagnets holding the cloud in place. and their error bars went down. But meanwhile, the people doing the beam measurements are also improving their stuff. Nobody knows why there's a difference, and they don't know what to do about it, even though it impacts our ability to predict the evolution. Now, we have a couple minutes, 5 minutes. Let's talk about concordance. So I just showed you this. This is what we get from cosmic microwave background. We'll do this more next time, but this is the so-called concordance. So, here's the cosmic microwave background data, and here's what it says about how much matter is in the universe. Dark matter and us matter. Protons and atoms and bananas. So this curve, by itself, it doesn't tell you much. It just says the universe is somewhere along this curve, and what is on this scale? It's the amount of dark energy in the universe. So if you just had the cosmic microwave background, you just have this orange wedge. But the acoustics that we get, the spacing of the bumps in the microwave background, that's on this green curve. So if you just imagine, forget about the blue for a second. So if we take the height of the bumps, we're somewhere here, and if we take the spacing of the bumps, we're somewhere here, and where those intersect, we have narrowed things down. And notice, if you go to the spot where those intersect, you're here at about 35% or so of the universe is matter, and about 70% of the universe is dark energy. Then, something we will talk about next time, I think, because we're going to run out of time. Oh no, we're going to go a little late if you can. We'll go away 5 minutes or so. This comes from supernova events. There's a special kind of supernova. I have to make sure I hold that the cap is on, otherwise I'll write on the screen. Supernova type 1A. These are called standard candles. Years ago, I worked for the Navy. Between undergraduate and graduate school, I worked for the Navy for a few months, and I was doing acoustics in the ocean. And one way to calibrate the distribution of microphones that we were hanging from the ship was we had a big box of light bulbs, and we had some bricks. Now, light bulbs are produced with precision. We would tie a light bulb to a brick and drop it in the ocean and wait. And the light bulb would settle down, and eventually the pressure would break the light bulb, and the microphones would hear that. And the depth at which that happens is very predictable. And we can calibrate our microphones using that technique. Well, that's what these type 1A supernova events do. We understand the chemistry, but we understand from the chemistry of a stellar explosion if it's a type 1A or a type 2 supernova. The debris, the guts that come out when the thing explodes, lets us classify different categories of supernova events where stars explode. Because they're standard, we can calculate how far away they are. They have the same energy. The ones that happen all over the universe have the same energy. So the distance scale, we only touched on this briefly in lecture 1, when we have the so-called distance ladder. These events are thought to be reliable measures of distance because they all put out the same amount of energy. And when it happens, really interesting, because there's no energy coming out of this star, except, it's a star. And then all of a sudden it does that. And then over a period of days, it does that as a light curve. It gets really bright and then it fades away. And while it's bright, a bright thing is easier to measure in a telescope by looking at the contents, the spectra tell us the contents, what elements are there, and so you can classify these things. So the supernova guys produce this curve for the amount of the universe that is us stuff And how much is dark energy? And where these things